So today we're going to lay down some material that will allow us to answer the question of what kind of extremum have we found. Right, remember last time we were able to find places where the maximum and minimum might be, but we weren't really able to say anything immediately about what kind of extremum we have found. Okay, so today we're going to put down some theory that will allow us to answer that ultimately to answer that question. But actually, it's theory that will be important for the entire rest of the semester. Okay, so what we're going to say today is really crucial. Okay, so we're going to get up to the mean value theorem, which is, I would say, the most important theorem in differential calculus, and maybe even the most important theorem in calculus. Okay, so that's not quite true, but almost the most important theorem in calculus. Okay, let's remember where we were. What we said was that we had this thing, Fermat's theorem, right? Fermat's theorem, which basically said that if f is differentiable at c and f has a local extremum at c, then the derivative there is 0. Right? F is differentiable at c and f has a local extremum at c, then the derivative is 0. And you remember, actually, the way we phrased it last time was if f is defined in an open interval around c. Okay, if f is defined in an open interval around c, differentiable at c, and has a local extremum at c, then its derivative is 0. Then yes, Madeline.
Can that criteria being defined on the open interval around c include even like big enough to be near infinity?
So are you
like
asking
the whole function?
Are you asking if the function is defined on the whole line? Mm-hmm. Is it defined on an open interval around that point?
Yeah, like is that implied?
Sure. I mean, if you're defined on the whole line, then you're certainly defined on an open interval around that point, right? If you suppose your function is defined on the whole line, well, then it's certainly defined in an open interval around that point.
Because sometimes in the book, it doesn't give you a domain or it doesn't give you any restrictions. So I was just wondering if that's just implied that your open interval then around c is
No, it doesn't. You're not saying that your open interval is the entire line, just that you're defined on some open interval around there. Okay. Okay. So you definitely don't have to be defined on the whole line for this to happen, right? You could have something like this, right? That function is not defined on the whole line, but it's at this point, it's defined on a small interval around there, and the derivative is 0, right? Doesn't have to be defined on the whole line. Yeah, just on an open interval around C. Okay, but actually, let me just sort of eliminate this, because when we talked about being differentiable at a point, that sort of includes the that being defined on an open interval around that point is included in that. Okay, so you can just leave that out if you want. It's basically already built into this part of the statement. Okay, so let's just leave that out. Okay, so if you're differentiable at a point, and you have a maximum in there, then you're guaranteed to have a 0 derivative there. Okay, and sort of phrasing this backwards, right? If f has a local extremum at C, and if f is differentiable, so So let's think like this. Suppose you have suppose you have a local extremum at C. If your function is differentiable there, well then by the previous theorem, then you know that f prime there is 0. So there are two possibilities, right? If you have a local extremum at a point, well, either your function is differentiable or it's not differentiable. Right? Let's put this as like case 1 and case 2. Right? If you're differentiable there, then the derivative will be 0. If you're not differentiable there, if f is not differentiable, then there's sort of two possibilities. One, either f is not defined in an open interval around C, or it is, f is defined. It is, but f prime is not defined there. Okay, so just to sort of lay out the logic. Okay, does this make logical sense to people? Okay. So, but the way you want to think about this, the main thing I think is to think like this. What this theorem gives you is that if you have a local extremum there, then either you're differentiable, and in which case the derivative is 0, or f is not differentiable at C. Okay. So those are the two possibilities, and you can break those possibilities down further, but basically those are the two possibilities. Okay, and so that gives motivation. That basically gives rise to a certain definition. We call C a critical point. Critical point if either f prime of C is equal to 0, or f is not differentiable there. Okay. So consequence. So here's the theorem, and here's the consequence, right? And you can rephrase the consequence by saying, if you have a local extremum, then you're a critical point. So the local extrema can only occur at critical points, right? That's basically what this is saying. Local extrema can only occur at critical points. Okay, and so that's what gave rise to the method that we were using last time, right? If we know that there's a critical point, what we do is we look for, if we know that there's an extrema somewhere, we say, well, the only place it could happen are at these critical points, so let's find all the critical points and then go from there. Okay, so that's what gives rise to your first move in looking for extrema. Your first move is going to be, let's look for the critical points, because we know that the local extrema can only occur at critical points. Okay. Is this making sense? Yeah, Mariah.
Are there critical points if it's in a closed interval?
Are there critical points if it's in a closed interval?
Or do they exist in closed intervals?
Yeah. So something, for example, so somebody gives you a function and says, somebody gives you a function on a closed interval. So this is valid on any interval. This statement doesn't say your function is given on a closed interval or an open interval or on the whole line or anything. It doesn't say anything about your domain. Okay, there's no restriction on your domain here. So given any function, what you do is you'd say, okay, what I'm going to do, I'm going to look at the critical points. I'm going to find where the derivatives are 0. And I'm going to find where the derivative is not defined. Okay. Well, here, A and B, the endpoints are places immediately where the derivative is not defined, right? Because we don't have, we have only half the side of the derivative. Okay. Right. So A and B are in here, and then it would pick off these 2 points, right? It would pick off. You'd say, oh, and here are places where the derivative is 0. And so those are the only places where a maximum or minimum might occur, right? And indeed, those are the places where the maximum and minimum do occur. Is any confusion about this? Yeah. Anyone want to talk more? There should be more talk. Yeah, I once taught a class by just showing them the videos from the previous semester, and then having them come in and talk about math. This proved to be really stressful for everybody because people weren't used to talking about math, right? But in fact, you should be able to talk, about math just like you talk about, whatever Foucault or whatever, right? It's not. I don't think it's any less. I don't think Foucault is any less complicated, right? And yet, yet people feel perfectly, well, at least somewhat comfortable coming in and trying to say something about it. Okay, maybe you don't feel comfortable. But at least you try. At least you try. So, I remember. Yeah. Okay. So anyway, so I feel like you should try to. It's a good thing. I think it's a useful skill to be able to talk about math. Math is certainly a subject of conversation like anything. Any other field could be a subject of conversation. Okay. And it's a bit strange that it's not taught in that way. Okay, so that is sort of sketching out what we did last time. Now this time, let's go on to the most important theorems. Oops. Yeah, so I should say that the scores in that class were extremely high. Extremely high, far higher than any other class.
What level was it?
It was a pre-calculus class, pre-calculus. And the scores were almost perfect, I'd say. Everybody in the class was almost getting perfect scores. However, when polled, they all hated it. And so 3/4 of the way through the term, I switched back to the normal way. And then the scores dropped. But they were happier.
When did they do homework, though?
At home.
So they watched your videos and did homework?
That's why they hated it.
Yeah.
Because there was like too much work at home. Because they had to watch the video and do the homework. And they come in and talk about it. Yeah, but the scores were almost perfect. Okay, so here we're going to start off with something called Rolle's theorem. Rolle's theorem. Okay. And it says this: if you have a function on AB, on some closed interval AB, and you know that the function is continuous on AB, to differentiable on the interior. So on the open interval, it's differentiable on the open interval, AB. And you know that the values at the endpoints are equal to each other. Okay. If those three things happen, then something happens. Does anyone know does anyone know or can anyone guess the conclusion of this? If you have a function, you know that the values at the endpoints are equal to each other. You know the function is continuous on the whole thing, and it's differentiable on the interior of it. So it's continuous function, and it's differentiable on the interior. It doesn't have anything like this. It doesn't have any cusps. Yeah, come on.
There has to be an extreme
There has to be an extrema. Well, actually, we know that from the extreme value theorem, right? Because you're continuous on a closed interval. So you're right there, the extreme value theorem tells you, there exists a max and there exists a min in that interval. That's good, but that's good, but we don't need all this other stuff to accomplish that. Yeah, right.
I have a question.
Yeah.
So, is there any chance that a critical point will be not a local or max or min? It just won't be anything.
Yeah. So we had this thing last time. F is x cubed and prime is x squared. So a critical point occurs at 0.
Oh, right. And
Right, but that's not a max and it's not a min.
Okay, thank you.
That's certainly possible, right? Yeah. So the critical points include the possible maxes and mins, but they are not necessarily maxes and mins. Yeah. Can anyone guess the conclusion? Yeah, tell me.
F prime C equals 0 at some point in the interval.
Yeah. Okay. So there's some point. There is a point, and there may be more than one. C in the interior where f prime of C equals 0. There is a point where f prime equals 0.
Isn't that the same thing as saying that there has to be an extreme?
It's closely related. It's not the same thing, right? Because there's a point where the f prime equals 0. Does that mean that there's an extremum there? No. But there's a point where an extremum occurs. Does that mean that f prime is equal to 0?
No.
Yes. No. Right. So you have to think about it a little, and there's a little. So you're right. Certainly, if the max or min occurred inside, right? If it occurred inside the interval, then that would be the place that you're talking about. That would. So you know that there is a max there. There is a max and min somewhere, right? If it's not at the endpoint. If it's not at the endpoint, then what? It's going to be in between the two, and so what does that have to do? What does that have to do with f prime being 0? Will f prime be 0 there? Sure, by Fermat's theorem. By Fermat's theorem, right? So Kimaya, yeah.
What's the difference between Fermat's theorem and Rolle's theorem?
Yeah, so Fermat's theorem, remember, says that if f is differentiable at C and a max or min occurs at C, then the derivative there is 0. Okay, and this is saying that if you're continuous on AB, differentiable on the inside, and f of A equals f of B, then there's a point on the inside where f prime is equal to 0.
Okay. But it doesn't necessarily have to be a maximum.
There'll be there's a connection. Yeah, there's a connection. So let's go ahead.
Which of the 3 clarifications cancels out the idea that it's just a horizontal line?
None of them. So it could well be a horizontal line. So yeah.
With
So
infinite
right.
extreme.
Right. So if you could have a horizontal line, right? You could have a horizontal line, right? You say, well, that's continuous on AB, that's differentiable on the interior, and f of A equals f of B. Is there a point where f prime is 0? In fact, every point is on the interior f prime is 0.
Okay, so there's multiple C's then.
Yeah. So there's one point. We're not saying that there's only one point.
Okay.
Yeah. So you have to when mathematicians say there is a point, they're not excluding the possibility that there's more than one point. If there's only one point, you say this: there is one and only one, and only one, one and only one,
So dramatic.
which is often abbreviated as one.
That's so weird.
Okay. Okay. People, we often have this phrase if and only if, right? If and only if, which you can guess the abbreviation. It's if. Right? Yeah. Okay. Right. Right. Like. Okay. So yeah. Okay. So yeah, you guys are talking. This is great. Right. So you've got all the pieces actually. You're putting all the pieces together. So there's a couple of possibilities. Right. So Madeline, I think, noticed that. Well, look, you know that there's an extremum somewhere, right? If that extremum is in the interior, then you found your point. Right. So let's put that as case one. Suppose, so let's say it like this: the extreme value theorem. By the extreme value theorem, we know there exists a min in AB. There exists a max in AB. And there exists a max in AB. Okay. We know that there exists a max or min there, and if either one occurs inside in the interior, right? Then we're done, right? Then Fermat's theorem. F prime at that point is 0. Right. Here's the picture. Right? If one of those guys, in this picture, the mins are at the endpoints. I'll let you copy down. So here's the picture. In this picture, the mins are at the endpoints, and the max occurs inside. Right. Right. You could have something like this. Both max and min occur inside. That's even better. We've got now we have 2 points where it occurs. Right. In any case, you at least have one of the guys on the inside, and by Fermat's theorem, well, the function's differentiable there, and a local max occurs there. So you know that the derivative is 0. Right? That's what Fermat's theorem says. Okay. So if that happens, if one of them occurs in the interior, then you're done. Right? Then you just say, well, that's the point that I'm looking for. Done. Okay. So it's like we said, this is pretty closely related to Fermat's theorem. It's like a consequence of Fermat's theorem. Okay. Now suppose first case, either one of these things occurs on the inside. What's the logical opposite of that?
Something occurs on the outside.
Say it again?
An extrema occurs on the outside.
The extrema only occur on the endpoints, right? Right. Right. First we say, well, either one occur on the inside. Well, if that's not true, then neither of them occur on the inside, and they were both on the endpoints. Right. So that's case one. But if otherwise, both must occur at the endpoints. Both the max and the min, must occur at the endpoints. Right? In that case, that brings us to Gwyneth's case, right? Because both the max and the min are going to be at the endpoint, but what do we know about the endpoints? They're equal. That says that the max and the min have the same value. So your function is?
horizontal line.
is a horizontal line. So the max equals the min. Right. 6 f of a equals 3. And f is constant. F is a constant function. Right? But if f is a constant function, then every point, at every point where the derivative is defined, the derivative is 0. Okay. So, right, so there's only two possibilities, and in either case, you know there's a place where the derivative equals 0. Okay. And so Rolle's theorem is proved. It's proved. Yeah, Mariah.
Wait, so if f of a didn't equal f of b, you wouldn't, there could still be a point C, but you wouldn't be able to be sure. Like the two endpoints have to equal each other in order for you to be sure that there's a point C.
Yeah. And you see what the trouble is, right? If it's like this, then you're not guaranteed a point where the derivative is 0, right?
Yeah.
Here, there's no place where the derivative is 0,
Yeah. Okay.
right? So you really do need f of a to be equal to f of b to have this consequence.
Okay. But you could have a function that's like wavy in between.
You could. So it's not saying that if this doesn't happen, then you don't get this. It's not saying if and only if. It's saying if this happens, then this happens, right? But it's not an if and only if. Yeah. So it's like saying, if you are Chinese, then you're a human being, right? But it's not saying if and only if. Right? You're Chinese if and only if you're a human being. Right? That would be saying that if you're a human being, then you're Chinese. How are you? Or I should speak to you in Chinese. Okay, so there's a difference between saying if this happens, then this happens, and this happens if and only if this happens. Okay. Okay. Rolle's theorem. Everyone have an idea about it? Okay. So, it says that if the endpoints are equal, then you're guaranteed a place where the derivative is 0. You're guaranteed a point in between where the derivative is 0. The derivative is 0. Okay. So now. Now let's get to what I'm saying is the most important theorem, at least in differential calculus, the mean value theorem. So again, you have a function on a closed interval, closed and bounded interval AB. If f is continuous on AB and f is differentiable on the interior, but you don't say anything about what happens on the you don't say anything about what happens at the endpoints, and something else happens. Does anyone know this? Does anyone know the mean value theorem? Either from previous course. Go ahead, Kelly. Do you know it? Yeah. Yes.
Equals f prime c.
Yeah. So right. We just said that it's not. We certainly can't say that there's some point where the derivative is 0. Right. There's no here in this picture. There's no place where the derivative is 0. But we can say something like this. It turns out we can say there exists a point C in the interior where f prime C equals f of b minus f of a over b minus a. That is to say, there's a point where f prime equals the slope of the line through the endpoints. Okay, or in terms of physics, right, if f is position, then what's this saying? There's a point where the instantaneous velocity equals the change in position over the change in time. In other words, the average velocity. Okay, there exists a time where instantaneous velocity equals the average velocity over the interval, over the whole interval. So you can think of this geometrically, you can think of this physically, think of it just as a statement about a function. Okay. Any questions about the statement? Okay, so the proof is pretty clever. You say, well, look, I have this function, right? And what I'm trying to do is find a point where the derivative equals this slope, right? So in your picture, it looks like the slope, the point is somewhere around here. There's going to be some point where the slope of the tangent line, right? Slope of the tangent line equals, you're looking for the place where the slope of the tangent line equals the slope of the secant line through the endpoints, right? Here's my secant line, and maybe there's some point over here where the tangent line has the same slope as that slope. Okay. Right? But how do you find it exactly? How do you find exactly that point? And so the trick is to do this. You say we're going to use we'll use Rolle's theorem to obtain the mean value theorem. Yes, Claire.
Will the point that's parallel or has the secant line always be on an extremum?
Not at all, right? Because the extremum is where at the
that's
extremum
rooted
the
zero.
slope would be 0.
Never mind.
Yeah, so in fact, never, unless the endpoints were at the same height. Yeah. Yeah, right.
Then how does this help you? Is this just kind of like a random point then?
Yeah, how do you get this point, right?
Or why do you want it?
Why do you want this point? Well, maybe you're interested in this sort of thing, right? Where you want to know where the slope of the tangent line equals the slope of the secant line.
In case you're wondering.
In case you're wondering. Yeah, in case you're wondering. I guess the importance of the mean value theorem isn't really evident at this point.
Okay.
But by the end of the term, at the end of the term on the final, I always put a question: what was the coolest theorem in this course? And last semester, I got all these people who said the mean value theorem because it showed up everywhere. It implied everything in this course. So it may not seem that exciting at this point, but in fact, it's really exciting. Okay, so we're going to use Rolle's theorem to get the mean value theorem, and here's the trick. So Rolle's theorem, you'd like to have a function that has the same values at the endpoints, right? We don't have a function like that here. So we're going to make one. Okay, we'll make a function that has the same values at the endpoints, and here's how we're going to do it. Let L of x be the secant line through the endpoints. let L of x just be the line. So giving it a name, that's what, just the line. Let L of x be the line that passes through those endpoints. Okay. Here's the graph. Okay. And now let d of x be the difference between the function and the line. Okay. D of x is the difference between the function and the line, right? And you see that, you know, what's the value of d at the end? What's d of a? What's d of a? 0. What's d of b? 0. Right? It sees that d is differentiable, it's continuous, line AB, differentiable, line interior, and d of a equals d of b.
Can you say one more time? Figure that out? What is?
Why d of a equals d of b? Well, d is the difference. D is the difference between f and L, right? And at A, f and L have the same value,
Okay.
right? And at B, f of B and L of B have the same value, right?
Oh.
So it's a difference, right? Like at each point, if this is x, I'm going to look at I'm going to take f of x minus d of x, right? So if I graph this, it would be 0 here and 0 here, and kind of get bigger and then get smaller, and then get bigger and then smaller and bigger. So this is sort of the graph of B.
Okay. That makes sense.
So, so what are we going to do? Who can see the end? Kelly, go ahead.
Well, since d of a is equal to d of b, use Rolle's theorem, and you know that f prime of c, or there's a point c where f prime of c equals 0.
Yep.
And since you know that, and you know that d of x is the difference between
Yeah.
f of x and L of x, you
Yeah.
can derive f prime of c.
Yeah. So what's f prime of c going to be? It will be the same. It will be.
Difference between f of x and L of x over. Yeah, like so it would be f of a, or it would be d of a over d of b minus d of b over b minus a.
You almost have it. You almost have it. So good. So apply Rolle's theorem. So Rolle's theorem says. Rolle's theorem says there's a point where d prime is 0. There's a point where d prime is 0. Right? Well, d prime is f prime minus L prime. Right? D is f minus L. D prime is f prime minus L prime. Right? So that tells you that f prime minus L prime equals 0. Can anyone see the end now? Clear.
So does that mean that f prime equals L prime?
Yes. And what's L prime?
So that's it's basically saying that the derivative of that point of the point, I guess C is the same as the secant line.
The slope of the secant.
Yeah.
Right. So, in other words, f prime c equals L prime c, but the slope of the line is f of b minus f of a over b minus a. Okay, so you found the point, you found the place where the slope equals the slope of the tangent line equals the slope of this secant line. Okay. Megan, do you have a question? No? Okay. Does anybody have a question?
I'm not sure what we've proved.
What we've shown is that there's a place where, remember what the goal was. We're looking for a point where the slope of the tangent line equals the slope of that secant line. And what we said was, okay, let's look at this this difference function. By Rolle's theorem, there's a point where the difference function has a slope of 0. Right? And that turns out to be the point that we were looking for, because the slope, the derivative of the difference function is the derivative of the differences, right? And we said that that's equal to 0. So what we found is a place where f prime c minus l prime c is equal to 0. That's to say, we found a place where f prime of c equals l prime of c. Right? If f prime of c minus l prime of c is equal to 0, then f prime equals l prime there.
Okay.
Right? Because you have, right, if a minus b is equal to 0, then certainly a equals b. Right? So just move the l prime to the other side. Right? So we found a point where f prime of c equals l prime of c. But what's l prime of c? L prime of c is the slope of L at that point. But the slope of L is constant, right? The slope of L, we know what it is. It's f of b minus f of a over b minus a. Okay, so we found a place where the instantaneous velocity equals the average velocity over that time interval. Let me put up something that you could also show using the same sort of trick. Okay. Suppose you have two functions like this, and they have the same endpoints. So I have two functions, f and g. Okay. Tell me something about these functions now, using the same idea. Can anyone? This is a challenge. Can anyone tell me anything interesting about these two functions? If they start at the same endpoints, then Stefano.
They have the same average velocity.
They have the same average velocity. Okay. Can anyone say more than that? Mariah?
It would be over the same interval, right?
Over the same
it's
interval?
Same instantaneous velocity.
So what?
So would that be the same instantaneous velocity? Because wasn't instantaneous average over interval?
So certainly we know that there's some point for f where the instantaneous velocity equals that average velocity. We know that there's another point for g where the instantaneous velocity equals that average velocity. But do we know that it's the same point? Actually, we do. Go ahead, Kelly.
We know it's the same point because of like what we just proved on that slide.
Exactly. Basically, the same thing. Now you say, well, consider d equals f minus g. Right? Consider the difference. Right? It's 0 here and 0 here. So there's some point where there's a point where d prime c equals 0. In other words, there's a point where f prime of c minus g prime of c equals 0. So if you have two cars and they start at the same point on this track, and then they go back and forward and end at the same point on the track, there's some point in the middle where they're traveling exactly at the same speed.
So there's some point
In
on
time.
both those lines where the slope's the same.
That's right. That's right. I can't see it, but but there's some point where that is guaranteed to happen.
Okay.
So that would be true for any two functions that have the same endpoints. That have the same point c, is where they have that instantaneous.
That's right. There'll be some point where the instantaneous velocities are identical. One can go a little bit farther, actually, and say, what happens if you have two functions that, you have one function that goes like this and one function that goes like this? Suppose that they don't start at the same endpoints. What can you say about them? That leads to something called the generalized mean value theorem. And the generalized mean value theorem gives you so-called L'Hopital's rule, is what gives L'Hopital's rule, for those of you who've seen calculus before. So the generalized mean value theorem is L'Hopital's rule. So anyway, so in any case, this theorem here that we have, the mean value theorem, is going to be the most important theorem, I'd say, in this course. Okay, so I think I'll have to adjust the homework. We didn't get through everything about the mean value theorem that I wanted to say, so I'll adjust the homework slightly, but it will be roughly what?
Will you be giving a practice example for a test on Friday?
The test on Friday. Right. Yes. Yes. Yes, I will. Yes. I will.